Swedish astronomer Erik Holmberg must have felt a surge of pride as he watched two swirling galaxies sideswipe each other in his lab at the Lund Observatory in 1941. Scarcely a year earlier, he had conjectured that a pair of galaxies could deform one another as they passed in space. And now, in the complex arrangement of movable lights before him, the 33-year-old scientist possessed a model that brought his idea to life. Flouting the astronomical wisdom of the day, which held that galaxies form in splendid isolation, Holmberg suggested that a galaxy can take shape in response to the fierce gravitational forces of other galaxies passing nearby. No galaxy is an island universe, he insisted. Instead, each is apt to collide eventually with its neighbors, inflicting cosmic scars that linger briefly in the form of spiral arms. To support his view, Holmberg crafted a laboratory model capable of reenacting the stages of these extraordinary pas de deux. He knew it was possible to calculate the gravitational effects, called tides for their tendency to ebb and flow, that arise when one galaxy crosses the path of another. But in the pre-computer days of the early 1940s, the volume of pencil and paper mathematics required to produce an answer made the exercise impractical. However, as he reported in the November 1941 issue of the Astrophysical Journal, a solution has been found by replacing gravitation by light. The validity of such a substitution, indeed, the success of the entire simulacrum, hinged on the fact that gravity and light diminished to the same degree over a given distance, a property described by the inverse square law of physics. Holmberg therefore stood on firm scientific ground as he represented the myriad stars of a hypothetical galaxy in the simplified form of 37 tiny light bulbs arrayed in 4 concentric rings. The brightness of the bulbs, which had been specially designed and manufactured so that their intensity would hardly vary, stood for the mass, and therefore the gravitational pull of the stars in the system. To achieve an accurate distribution of mass throughout his model, Holmberg extrapolated from stellar observations showing that the surface brightness of a galaxy rises rapidly towards its center. He attained a similar effect by graduating the voltage supplied to each ring of lights. The inner 2 circles burned with a candle power of 1, while the third ring burned at 0.7 and the outer ring at 0.3. He then fashioned a second mock galaxy the same way. Mounted on a table covered by a grid, the 2 sets of custom-made bulbs could be inched along in a step-by-step mimicry of what Holmberg imagined must occur when a pair of galaxies pass in space. As those movements were made, an array of photocells measured the minute fluctuations in the amount of light reaching the boundary of the grid. The photocells translated these optical signals into electrical signals and forwarded them to a second bank of instruments known as galvanometers, which charted the rising and falling of current levels with precision. In theory, the variations in these readings would mirror the gravitational tides that course through galaxies in collision. Holmberg's experiments led him to conclude that given the proper conditions, one star system could capture another during their intergalactic dance. The gravitational tides created by the mutual tugging of the 2 galaxies would bleed energy from their orbital motions and force them into ever smaller, ever closer orbits. Have a great day.